Hello, this is Greg Schultz with Charged Magazine, back for another conversation. For a few years now, Charge has been reporting about how dry electrode coating processes have the potential to revolutionize battery production through a reduced solvent, energy, and footprint demand. And lately, we're seeing more and more announcements about new developments. So, to learn more about the state of the technology, we thought we would chat with some experts in the field, which is exactly why we have Tejas here from Chemours. Tejas, if you wouldn't mind, give us a walkthrough, a little bit more detail on who Chemours is, what you do with the organization, anything that's going to help our audience understand your company a little bit better.
Sure. Thanks, Greg. And I would like to thank you and Chris and ChargedEV for having us participate on this session as well. So my name is Tejas Upasani. I'm the Global EV Technology Manager at Chemours. I've been with the company for about 6 years, and primarily I'm responsible for the technology and innovation in the EV space of our clean energy venture. For my background, most of my background has been in polymers and elastomers and serving various types of role in primarily the automotive market. We like to call Chemours as a startup company with 200 years of history. So we spun out of DuPont in 2015, and we have leading brands throughout various types of industries. So Chemours particularly is into three business categories. One, we have the advanced performance materials, then the thermal solutions, and the titanium technologies. So I reside in the advanced performance materials business, which is APM for short. And within the APM business, we have many different power brands, which you could recognize as Teflon, Nafion, Viton, and these have been serving, many of the semicon or automotive industries for a long time. So like we have done in the past, we are experiencing a growth in our products in a brand new field, which is the dry electrode process, and really excited to see how an old product finds new application and completely exciting way of putting it into an application. So extremely excited to talk about this.
Awesome. So, since you mentioned it, can you walk us through the basic advantages of the dry electrode coating process versus the traditional wet slurry-based process?
Sure. So before I jump into the advantages, what I'd like to do is give a little bit of a flavor of what the dry process is. So essentially, the dry coating process is a novel way of manufacturing cathode and anode electrodes in the lithium-ion batteries. So in the traditional process, which we would call, the wet slurry process, we have the active ingredients, we have the conductive additives, and we would use a particular binder, which needs to be dissolved in a solvent. Once all these ingredients are mixed together, then we create what is called as a slurry. And that slurry has to be coated onto a current collector. And at that point, really the function of the solvent is done. And so we dry off the solvent and we get a nice coating on the current collector. So that's like the traditional way of making the wet slurry coating. In the dry process, really many of the ingredients, they remain the same. So we'll have similar active materials, we'll have similar conductive additives. Now, what really changes is the binder. So in this case, we'll be using Chemours' Teflon PTFE. And because of the unique properties of the Teflon PTFE, it really doesn't need to be dissolved in any solvent. It can form the coating as it goes through the processing steps through a process called as fibrillation. And so that basically forms the entire coating on the current collector. So whether it's cathode or anode, both of these can be enabled by this particular coating process. Now, if you look at the advantages of why is the dry process advantages over the wet slurry process, at a high level, we can look at this from three different angles. One is going to be that it is much more environmentally friendly It gives a higher sustainability factor as opposed to the wet slurry process. The second aspect is going to be it reduces the overall production cost of manufacturing the lithium-ion batteries. And the third aspect is really it also enables a better performance of the lithium-ion batteries. So when we look at the environmental friendliness, the wet slurry process uses NMP, which is a toxic solvent. If there is no need for the solvent, then inherently, the hazards associated with the solvent are removed. So which naturally helps us to make it a very environmentally friendly and safe way of making those electrodes. And the second part is the production cost. So if you look at just the footprint of how much space is required in order to make the wet slurry process as opposed to the dry process, by some estimates, it's like 10 times the excess space that is required in order for wet slurry process. So there's a tremendous amount of savings of the floor space itself that can be achieved with the dry process. And finally, with the dry process, we can enable making thicker electrodes, which can help with improving the power density and therefore improving the overall performance of the batteries themselves. So really, Chemours' PTFE is kind of at the core of all of this technology because of its inherent nature of forming those fibril networks.
Excellent. So yeah, I mean, this was something I was going to ask you anyway, but you kind of led me into it is, what are the advantages of the technical process in terms of making better EVs? But it sounds like increased range could be one of the benefits. Obviously, it's a more environmentally friendly manufacturing process, which is certainly something that manufacturers are going to care about. It's something they have to keep in mind. Is there anything else that you'd add to that in terms of how it's going to make a better finished product?
If you look at, making electric vehicles better and then looking at how the dry process is going to enable making the EVs better, then Chemours' PTFE is really at the heart and center of that process. So reducing the production cost is going to be really necessary in order to drive down the cost of the lithium-ion batteries, which essentially translates to reducing the cost of the EVs and enabling a wider adoption of the EVs. Secondly, as you mentioned, if you're able to improve the performance of the lithium-ion batteries, whether it's by extending the range of the driving or whether it is by accelerating the charging rates, all of these things are going to go towards making the EVs better.
Maybe you were just about to say this, but I was going to highlight it. So is this something that would help to reduce charging times potentially?
It potentially could. And so there's a lot of testing that is being done right now comparing the wet slurry process and the dry process. And so, even if we are able to go to a higher loading with the dry electrode process, so going from, all the way to up to like 8 or 9 milliamp hour per centimeter square, we are still able to see competitive or higher charging rates as compared to a normal loading of the wet slurry process, which is about 3 to 4 milliamp hour per centimeter square. Now, many of this work is done at lab scale or a pilot scale, but as the technology matures and as we start seeing better process technologies on a pilot or production scale, these can be realized into real life scenarios as well.
Perfect. Yeah, that was actually another question I was going to ask is if this is currently in production now, or if this is something that we're looking to get into production.
Yeah, it's kind of a mix of both, really. If you look at the wet slurry process, that has been going on for decades. So in the initial phases, there was a development phase that went there was a pilot scale and a mature phase of the wet slurry process. We are kind of in the similar phase for the dry electrode process, except for we are in the early stages of the development process. Some of the industry players, they are in production scale. So for example, on the battery day in 2020, Tesla announced that it wants to convert its 4680 production into a dry electrode process. And on the investor day in 2023, they actually announced that they have successfully implemented commercial production of the dry electrode process. So we know of that they are innovating in this space. They are invested in adopting the dry electrode process. And so similarly, we are seeing it in other areas and regions as well. PowerCo, which is essentially a subsidiary of Volkswagen, they have announced that they would want to deploy and commercialize the dry electrode process at many different locations. LG has announced similar plans. And so we think that many of the cell manufacturers and the OEMs in the next 2 to 5 years are definitely, they are going to be in different stages. Some are going to be the pilot scale, others are going to be advanced towards the production scale. But as it stands now, right now, we are seeing the entire spectrum of lab, pilot, pre-production, and production scale adoption of the dry electrode process. Recognizing the benefits of what comes with the dry electrode process, I think it's fair to say that it is coming pretty soon, and there is going to be a wider adoption of this in a production environment.
Excellent. So you mentioned, certainly some automotive players here. I've got to ask the question because our audience certainly there's a large contingent that are working on automotive products, but we also have a lot of folks that are working on electrified construction equipment, marine equipment, up to and including aerospace. So, I mean, this is a sort of technology that could be adopted for any of those use cases. Is that fair to say?
Exactly. Absolutely. And that's the beauty of this, is because it's a novel manufacturing process, right? It could be adapted to any different application. I mean, obviously, and the good thing is it's not relying on any particular aspect of whether the cathode chemistry or the anode chemistry. Anything can be applied for this application. So whether it is going to go into energy storage, whether it's going to be with lithium ion, sodium ion, whatever might be the chemistry, as long as there is a good process control and we are able to manufacture good electrode structures, the application is up to the consumer to adopt it in any of the different types of application. So imagine it's all the different applications that the wet slurry process currently enables. Those same applications are possible with the dry process, just in a sustainable fashion at a lower production cost and potentially with improved performance.
Yeah, I mean, it sounds like a tough sell. Most companies don't want to save money or be more environmentally friendly, right? It sounds great. So, that's obviously the kind of the good side of everything, but as with everything, there's hurdles. So are there any major technical hurdles or anything that we still need to kind of get past before this can be widely adopted?
Yeah, certainly there are hurdles, and as we call it, the growing pains, right? I mean, it's in the early stages of the development. So everybody is trying to understand how to make this process work. So there's no standard way of, okay, here's the equipment, here's the calendaring, here's exactly all the different aspects. You just plug and play and start the process. That is not there yet. Everybody's trying to develop the process setup, and they're trying to make sure that the correct mixing and calendaring can be done in order to create that uniform structure. So some of the technical hurdles that I could think about is, PTFE and the dry electrode process is enabled through this fibrillation network of PTFE. Now, the fibrillation network has been understood for decades. And, we as inventors of PTFE, we have invested a lot of science behind understanding the fibrillation network, but it generally has been applied to industries where PTFE is the dominant component in the application. So as an example, if you look at your standard plumber's tape, which is a Teflon tape that we call, it utilizes exactly the same principle of fibrillation of PTFE. And that's the reason why let's say in one direction, you can pull it really easily, but in the transverse direction, you can just break it apart easily. So it's the processing technique which enables a real good application. So it's the same in this application, basically, that You're trying to control the fibrillation through the mixing process and through the calendaring process in order to make a good electrode process. And so Chemours has invested heavily in developing various types of PTFE products. Then they can range from different molecular weights, different polymer architecture, and all of these are intended to enable the proper fibrillation characteristics within the electrode process. So controlling fibrillation is really one of the hurdles. And we are looking internally as well as working with industry partners in order to look at or analyze these fibril networks and structures to make a good electrode structures. So that's one technical hurdle. One of the other things is, and I think it's a well-documented fact, that PTFE may have challenges on the anode side. On the cathode side, generally, PTFE is oxidatively very stable. So even one of the advantages is that you can go to higher voltages and it still is stable at higher voltage applications. So on the cathode side, it's a very promising application. On the anode side, there might be reductive stabilities associated with PTFE. And so using traditional PTFEs might not be the optimum solution. And that's one of the reasons why internally we are developing a lot of different products in trying to understand what is exactly the mechanism of how PTFE is not stable on the anode side. And once we understand that mechanism, how do we solve that? And so there's a tremendous amount of work going on internally, and we are working with our external partners as well to try and understand, okay, these are the advantages or these are the results that we are seeing. Are you able to corroborate? Can you, in your systems, also tell us whether you're seeing those same results? So there's a collaborative work that is going on in trying to understand and solve many of these hurdles.
Excellent. Yeah. So in preparation for this, we did look into, what some potential hurdles might be, and just found kind of a list that, if you don't mind, we might fire off at you, and then you can
Sure.
kind of let us know how you see it. But one of the challenges that we saw is adhesion. So the dry material has to bond to the electrode surface, but the flat surface and lack of texture can make that difficult. So is there a way that is currently being addressed?
The industry right now is really using what we call as the carbon coated current collectors. And so they have certain coatings on the current collector itself. And when the dry process films are made, those get laminated onto that carbon coated current collector. So that's the solution that the industry has at this point, and it's working fairly well in both anode and cathode processes. Now, when it comes to, okay, if we wanted to directly laminate it onto the current collector without any carbon coating, then that's a little bit of a problem that we are addressing right now. It does require a little bit differences in product development. And so we are looking at ways of how we can alter the chemistry of the polymers itself in order to get a better adhesion to the current collectors. So adhesion is a challenge directly onto the current collector, but there is a solution available right now, which is basically the carbon coated collectors are being used, and they are they're working for the application.
So is there any disadvantage to that carbon coating that would kind of necessitate the development of the non-carbon coating solution?
I think there's a couple of ones. As industry matures, we are going to see every single place that the cell manufacturers and OEM want to reduce the cost. So if I'm able to directly laminate it onto the current collector, why have this carbon coated coating on that? So if you're able to not have it, then it reduces the cost of having to go to a carbon coated current collector. So that's one of the advantages of directly laminating onto the current collector. And so I think that might come, but there are other low-hanging fruits, so to say, that needs to be resolved before people start tackling pretty heavily into, let's say, the adhesion and going and directly laminating onto the current collector.
Yes, we may have just partially answered this, but another one we had listed here was inactive material. The process needs to reduce the amount of inactive material to a similar level as wet coating, but this can be expensive and hard to scale up. I mean, we may have somewhat addressed that already, but if there's
We
anything.
do, and yeah, and in certain chemistries, there is a need for increasing the inactive materials, and so especially on the cathode side. Whereas there are some chemistries where we are looking at less than 2%, and in some cases even less than 1% of the binder that is used. So it's already being worked on in trying to reduce the inactive materials pretty heavily. Now, it does require a lot of process optimization because, as you can imagine, this small amount of binder is holding up the entire powder chemistry, right? And so trying to make sure that the fibril network is designed or it is processed really well is the key. And so a lot of process technology, along with the material enhancements that we are doing in developing new materials and coming up with different polymer chemistries, is actually going to enable even further reducing the amount of inactive materials.
Excellent. Another one, uniformity. So the dry coating mixture needs to be uniform across large areas of the battery electrodes.
So uniformity, I don't think it is necessarily restricted to dry coating. In the wet slurry process, when we mix different ingredients, the idea as well is everything mixed uniformly. So there is methods that have been developed in the wet slurry process to understand, yes, the viscosity is right or the solids content is right. And so we know that will help us to understand that the uniformity of the slurry is also good. And when it goes on to the current collector, there are methods developed in order to understand that. In the dry process, it's similar, except for we are dealing with all the powders. So there are analytical methods and tools that are being developed in order to first understand how do we know that these powders are mixed correctly. So the active materials, carbon black and PTFE, all of these, they need to be mixed really homogeneously. So we are actually internally developing methods as well and working with partners, industry partners who are the world leaders in analytical tools in trying to understand how do we apply powder rheology in order to understand that the mixing has been done properly. So there is a little bit of method development that has to be done over here. And so we are working internally to develop some of those methods. So once the mixing is done homogeneously, the beauty of the dry electrode process is that once it is transferred onto the calendering rolls, and then the coating is done, you don't really have any movement or settling of the ingredients. As opposed to, let's say, if we in a wet slurry process, if you were to make a thick electrode, as the solvent is drying off, these ingredients, they may start to settle during the drying process. That really doesn't, because there is no drying of the solvent, there is no movement of these ingredients once the coating has been done. So the real key here is going to be the uniformity during the mixing process. And once that mixture is uniformly mixed, then to transfer it onto the calendering rolls and then enable a really good uniform electrode structure.
So getting the uniformity during the mixing process, would you say that's more challenging, less challenging, or about the same as doing so with the wet slurry?
I wouldn't say it's more or less challenging. I think it's just the natural process of understanding how do we mix these powders together. So at this point, if there are processes that are available, and these are batch process or continuous process, which each one of them has its own advantages of enabling a good mixing process. So the key is, how do you know that you've mixed it really well? We can mix and different processes are being applied, but to understand that we have achieved the optimum level of mixing, that is the characterization methods are really critical to understand that yes, mixing has happened really well, or some of the fibrillation network that needs to be developed during the mixing process that has been achieved as well. There are many of the industry partners and our internal work as well, which shows that when we are using specific PTFE materials developed by us, we are able to achieve really good homogeneity in the mixture itself. So there's a combination of process technology and the material properties, which needs to be optimized in order to get a good mixing homogeneity.
So, and is that something that, for example, your company would partner with the manufacturer on to determine, like, here's what we have found based on our materials. This is
Yep.
the ideal mix.
Yes. And so that is one of the keys that we wanted to do, is because throughout our history we have looked at application development. So we don't want to just here's a material and give it to the customers and use it, find out a way
Best of
to use
luck.
it. Exactly. We don't
Yeah.
want to be that kind of a partner. So and this is what we have done in Chemours for decades, to understand really the application and internally see if we were to do this, how would we do it? So if we were to put ourselves in customers' shoes and wanted to enable these products, how would we do that? That's what we are doing right now. And so there are methods available that to understand the mixing homogeneity which are very R&D based, which are you go into really the depth of understanding in an R&D environment, and we are doing some of that work. But really the key is, if someone is doing this on a regular production basis in a manufacturing site, they are not going to have time to take a sample, go into the R&D lab and wait for days in order to get the results before and years continuous production happening. So when we are developing these methods internally, we are trying to keep that in mind, that can we develop a method which is going to be inline production characterization and analysis. And so we already have some of those techniques developed, and we are actually working with some of our industry partners and getting their materials, testing it internally and seeing, okay, we have tested our materials. Can we now look at real life scenarios in an industry environment, see if we are able to analyze them in the same way that we are able to analyze? And we are finding those correlations pretty good. So we want to be, as Chemours industry partners, in trying to really solve the problem and enable the adoption of the dry electrode process. We want to say that we are just a supplier of PTFE. We don't want to stop there. We want to make sure that we contribute to the success of our customers as well.
Excellent. Just a few more here, and then we'll probably wrap it up. But the other, a couple more challenges that we've seen. So electrode quality. So battery materials, limited flow properties can lead to lower quality electrodes in terms of thickness, density, and electrochemical performance. What's your take on that?
I think it kind of is looking at the process technology and selecting the right PTFE in order to make sure that the mixing is done correctly, and then the mixture is then transferred into a good electrode. That is going to be the key in order to make sure that the density is right, the porosity is right, the entire electrode structure is uniformly developed, so that you don't have a thick electrode in the middle of the sheet, whereas you have thin electrodes at the end of the sheet. So all of these are really critical in order to expand on to scale up the dry process. So there is an element of the process associated with that, the equipment that is being used. And there's a lot of work being done on the equipment as well to understand how we are going to get really good electrode quality. So understanding the Chemours' PTFE, how it performs in these processes, and really making a good uniform electrode structure through the process equipment, I think is the key in order to get uniform electrode structures.
Excellent. So, can you tell us about Chemours' advanced fluoropolymer binders with Teflon PTFE?
Sure. Yeah. So as I mentioned, we have understanding the fibrillation characteristics is really the key in enabling the dry electrode process. And Chemours has developed different types of products for various industries for a very long time. And so that is really the key that the learnings that we are taking, even in this particular application. So we have a spectrum of different products which are available to understand how these are going to be applied in a batch mixing process, how these are going to be applied in a continuous mixing process. Not all of our customers are going to be having the exact same way of manufacturing it. So trying to tailor our products to their needs is the key. And given that we are the inventors and have tried all different sorts of chemistries for our PTFE products, it's easier for us to understand what exactly is going to affect the fibrillation characteristics, the aggregate sizes of that, how is particular chemistry going to affect let's say, the mechanical properties of these materials as well. So given the inherent nature of better temperature resistance, better chemical resistance of fluoropolymers in itself, I think it helps us to really understand what the problems are, to anticipate what the problems are going to be with our customers, and then come back to our labs and design solutions which are going to enable the dry electrode process. And so the combination of the history that we have with material development, with application development, and really connecting it with the customers is a key. And one of the benefits also is that Chemours is the only PTFE manufacturer who has manufacturing sites in all three regions. So we have in the United States, in Europe, as well as in Asia Pacific. So when we think about a scenario where the manufacturing is going to be scaled up into a production scale, then we do have the flexibility of having the products being made at different locations and supporting our customers with the same quality, the same safety standards, and same standards applied to responsible manufacturing.
Excellent. So, one last thing here. So, we've heard about some proposed regulations in Europe around PFAS and that could impact PTFE. What impact would this have on dry electrode coating?
Yeah, I'm glad that you asked the question because sometimes it is sort of the elephant in the room when we are talking with many of our industry partners. So, we as Chemours we firmly believe that PTFE can be manufactured responsibly, and we are in favor of industry-wide national regulations and testing requirements, which are basically based on science and facts, and they are data-driven regulations and testing methods. We are completely in favor of that. So when we look at the emissions that are potential for manufacturing PTFE, we spend incredible amount of time, money, and resources in understanding what are the sources of emissions, spend a lot of time in understanding putting abatement systems in order to control those emissions. And not only that, we are also engaging heavily in trying to understand what are the alternate manufacturing technologies to make our products better. So all of these are steps that we are taking in order to meet up with the needs of the regulation. Honestly, in general, if we look at the EU regulations particularly, it's not necessarily confined to PTFE only. PVDF, which is used in the wet slurry process, could also potentially be impacted by the same regulation. So I think fluoropolymers in general, they are very essential to lithium-ion batteries, and they're very essential for us to transition to a clean energy environment. So whether it's Teflon PTFE, which is used in the lithium-ion batteries, or our Nafion ionomers, which are used in the hydrogen economy, all of these fluoropolymers, they're They're absolutely essential in this transition journey. So I think we want to be partners in the regulation to make sure that the needs of the regulations are met, but at the same time, these products are manufactured in a responsible way. And we are totally committed to doing both of these things to support our partners to enable the dry electrode process.
That's excellent. Yeah, and we love to hear it. We're EV enthusiasts. We really appreciate you coming on and taking the time to speak with us on this. And we're big fans of anything that we can hear that's going to make an EV purchase easier on an end user, and hearing things that can help to get cost out in the battery manufacturing process, hearing things that are going to make the manufacturing process cleaner and certainly more efficient. We know the realities here that, it's currently somewhat expensive to get into it. We're big fans of anything that we hear that can help to address that, and then help to address any concerns about things like range and the impact of the manufacturing process. So very exciting stuff. We really appreciate you taking the time and joining us on this. And, with that, if you got anything else to add, or one other thing, where can people find more information on this if they'd like?
Yeah, definitely. So feel free to contact me at Chemours, but I would encourage your viewers and listeners to visit our chemours.com website. And it has a ton of materials for our products, especially in the EV. But at the same time, we also have a lot of material available on our efforts in sustainability as well. So I would like to encourage viewers to take a look at both of these things on our website, which is chemours.com.
And just so that everybody knows, how is that spelled?
CHEMOURS.com.
Outstanding. Thank you so much for joining us, and have a great rest of your day.
Great. Thank you, Greg. And I really appreciate the opportunity of coming on and speaking with you guys. Thank you.
Our pleasure. Thanks.